Okay, everyone, we were trying to have another person do a guest lecture today, but I'm going to just start the lecture and see if he can't join in at some point. So, today we are looking at exponent rules, and this is just a silly cartoon to get us started off with here. Say, Cube, do you consider yourself to be religious? And Cube responds, I believe there are higher powers than us, if that's what you mean. So that is what we were looking at, a little bit of exponents today. So exponents. An exponent tells us how many times that we're going to multiply a base by a factor. So you can see here we have a base of 3, and it is being raised to the 4th power. So that tells us we are going to take 3 and multiply it 4 times to get to 81. So that's just base and exponent. We say things such as 3 squared, 3 cubed, and as we continue on, we usually just say 3 to the 4th power, 3 to the 5th power, so on and so forth. So that's just giving you a little bit about bases and exponents, kind of the terminology. Sometimes I say the word exponent, and sometimes I also say the word power, raising it to a certain power, such as the 4th power. So you can look into that. All right. So some rules. There's a lot of rules with exponents. And the first rule, and a fairly basic rule, is that anything raised to the power of 1 is itself. So 3 to the 1st power just equals 3. X to the 1st power equals x. So anything to the 1st power equals itself. A rule that's going to become very important is the product rule. And what the product rule says is if I have a base A and I'm raising it to some power and I'm multiplying it by that same base A raised to another power, I can add those exponents. So for example, if I have x to the 4th power, x is my base, 4 is my power there, raised to multiplied by x to the 5th power, what I really have is x times x times x times another x, right? 4 x's there being multiplied. All of that times x times x times x times x times x, 5 of them. So we can see the reason that we add those exponents when we multiply is if we write it all out, we would have 4 x's times 5 more x's for a total of 9 x's. So that is the product rule of exponents. This brings us to the 0 exponent rule, okay? The 0 exponent rule says if I take something and raise it to the 0 power, that's going to equal 1, okay? Except for 0 to the 0th power. That does not equal 1. But in general, anything raised to the 0th power equals 1. So my question now is we're going to do a poll, and I want you to look at our 3 choices, A, B, and C here, and figure out which choice does not equal 1. Okay, which choice does not equal 1? Go ahead and poll in with what you think. Which choice, A, B, or C, does not equal 1? Okay, most people have pulled in. Linda, I haven't seen you pull in. I don't know, maybe you can even hear me. Yeah, so for those of you who can hear me, why don't you at least give me a smiley face or a thumbs up or something in our emoticon, or maybe you don't know where to poll. The polling is, if you look up above, you'll see a smiley emoticon, a person that can step away from the session, the raise hand, and then the polling gives you A, B, or C. And in that polling space, that's where you're able to plug in there. Okay, good. I see that you have polled. Thank you. So I'm going to publish our response here. Okay. So what we see here is that nobody chose A. Everyone recognized that 8 raised to the 0th power does equal 1. Okay. And then one person chose B and 3 people chose C. So B says parentheses 8k to the 0th power. What this is telling me is it really wants the whole thing here, 8k. This whole thing is being raised to the 0th power. So this also equals 1. However, in this last instance, only k is being raised to the 0th power. And again, it has to do kind of with order of operations, parentheses first, then exponents. And in this case, the exponent is saying k is to the 0th power. So that means I would have 8 times 1.
Hi, Maggie.
Or 8. Hi, Bob. Glad you're able to join us and figure out your glitches. Everyone, we have Dr. Bob Hoare with us today, who is going to continue talking to us about exponent rules. Bob, anything you want to add with the 0 exponent rule here?
No, I think you're doing a great job.
All right, here we go. So, Bob, can you help us through figuring out about the negative exponent rule?
Yeah, the negative exponent rule is one that does lead to some confusion. The negative exponent on there really implies that division is occurring rather than multiplication, which is what we see when we see 8 to the 5th. And to investigate that a little bit, let's use the product rule that we just learned to see that 8 to the 0 ends up equaling 1. So if we take 8 to the 5th, oops, I'm just going to turn my pen on, hold on. All right. 8 to the 5th times 8 to the negative 5. If we add the exponents, like in the product rule we just had, those two exponents sum to the number 0. So 5 minus 5, or 5 plus a negative 5, either way is 8 to the 0, and we just learned that that is 1. So if 8 to the 5th is not the number 1, which we know it's not the number 1, then 8 to the minus 5, this number here, must be of the same size as 8 to the 5th, but dividing it out. So the rule that makes this easy to remember, I believe, is that a negative exponent, something like x to the negative a, if a is some number, is the same value as 1 over x to the a. And just to see how that works in our example up here, let's go back and recalculate 8 to the 5th times 8 to the minus 5 by trading that negative exponent in for a 1 over x to the a situation. So we have 8 to the negative 5, according to this new rule, should be equal to 1 over 8 to the 5th. And I could now go back to this multiplication and rewrite it. This will be now 8 to the 5th times 8 to the negative 5, which we just rewrote as 1 over 8 to the 5th. And if I simplify that fraction, I see that the numerator and the denominator are the same. So I will end up with 8 to the 5th over 8 to the 5th, which is 1. And that helps me verify that this formula back here is accurate.
Yeah, so we can look further, and here's that formula Bob was showing us. That a to the n, or x, or a to the negative n, or x to the negative n equals 1 over a to the nth. So now, I'm using that idea, giving you a little bit more complicated idea I want you to investigate and poll. Which one of the following equals 1 over, parentheses, 5x squared? So go ahead and poll in about that, and then we'll let Bob talk us through what the differences are in A, B, and C. Again, using your polling feature, and just think about it, and then we'll help you through it. Hey, some people chimed in, not everybody, but I will go ahead and post our results here.
It looks like a little bit of everything, but B was the winner in the poll. What I'd like to do is walk through and talk about each one of these individually. The 5x to the minus 2, what we're about to do here is combine some of our previous knowledge, and this can get tricky when you're applying multiple rules to a particular problem. But the key question here is, what is that 2 that is on the screen in the original question actually applied to? And if I rewrite our answer A here without a negative exponent, then the way I would do that is using the rule that's up above. 5x to the negative 2, if I look at this piece here, is the 5 stays right where it is. That exponent is not on the 5, it's only on the x. So this would be a 5 times 1 over x to the 2, which is 5 over x squared, which is not the same as the original. So A is not the answer. And the reason A is not the answer, again, is because this negative 2 is being applied only to the x, not to the 5. So if we think about that, I need the 2 to apply both to the 5 and to the x. And that's what's going on in B. So I think we have a winner here. 5x to the minus 2, again, according to our rule, if we have a negative exponent on something, and these parentheses imply that that negative 2 is on the exponent on 5x, not just the 5 or just the x, but on 5x, we will get 1 over that same quantity to the positive exponent 2. So this would be 1 over 5x squared, which is what we were looking for. So success there, even if the pen's not working real smooth. The last one, part C, is similar to the problem that we had with A. It's a little confusion about what the 2 is being applied to. Although this one has a little something similar or different going on. If I rewrite this one, x to the minus 2 again has its value is 1 over x squared. So if I rewrite that and leave the 5 down there where it was, I'll end up with a 1 over 5x squared. The 5 is there, and the x squared is the value that x to the minus 2 becomes in the denominator. And again, comparing that with the original, the lack of parentheses down here is important. this 2 down here is actually being applied just to the x and not to the 5. So this quantity right here, sorry about that. My undo's not working either. The 2 is just on the x. So we end up with a 1 over 5 times, and I'm going to put the times in to emphasize this, the quantity x squared, which is not the same as the problem in the question. So we found B, we knew that was the answer when we went on to C, but the reason C is wrong is because of the location.
Good. Bob, if you want a thinner pen, switch from the highlighter to the pen. That'll give you a thinner line like I use. Just not there. Okay, so that is our negative exponent rule. And we have some more variations of these rules that Bob can talk through. We have 2 variations that are just extensions of the exponent rule. So take it away there, Bob.
Yeah, the first one here really is a fraction within a fraction. If I rewrite that one, the denominator we know from our previous rule is a 1 over a to the n. And so this complicated expression here is really a 1 over a to the n. And if I invert and multiply, the value that I end up with is a to the n over 1, which is just a to the n. So it's a fraction within a fraction, but basically what this tells me is that if I move something from the numerator to the denominator that has an exponent on it, the sign changes. So I combine the last rule with this rule, and that's, in my mind, the way I keep track of it. If I move something from numerator to denominator or the other way around, the sign on the exponent is going to change. And number 2 is a combination of that idea with 2 negative exponents. Again, the proof of this would be to take this expression on the left and rewrite the numerator and denominator using our definition of a to the minus n and b to the minus m. It would be a 1 over a to the n in the numerator and a 1 over b to the m in the denominator. And again, it's a fraction within a fraction. So if I invert and multiply, then I end up with, in the numerator, this will end up coming all the way up to the top. I end up with a b to the m on the top and an a to the n in the denominator, which is the expression that was given on the screen. So again, if I think about the a to the minus n is pushing the a to the n to the denominator, and b to the minus m is pushing a b to the m to the numerator, then that idea of moving from top to bottom, changing my sign on my exponents, works even when things get a little complicated. The examples down below then test to see if we know what's going on there. Maggie, do we want to poll on this or just walk them through it?
No, go ahead and walk them through it.
Okay. So in this first expression, this one, pretty straightforward. It's a 1 over 4 to the minus 3. So again, in my mind, there's a 4 to the 3 coming up to the top. There's nothing else in that, so this must simply be 4 to the 3. In the other expression, in number 2 here, we've got a 3 to the minus 3 in the numerator. So that'll end up moving to the denominator if I want a positive exponent on it. And the negative exponent in the denominator will push x to the 2 up to the numerator. And again, these are equivalent statements, so you can rewrite one as the other anytime you want. Typically, we get confused a little bit with negative exponents, so often when you see a problem that says simplify in it, one of your goals is to remove negative exponents, and this shows you how you can manipulate that without changing the value. Any questions on that?
Okay. So just to recap, we've gone through 4 exponent rules. There's a lot of rules in these. The exponent rule of 1, anything to the first power is itself. We went through the product rule, which is the idea of when we're multiplying like bases, we add the exponents. The exponent rule of 0, anything to the 0th power is 1, and then our negative exponent rule. We've already been through 4 of these exponent rules, but we've got 4 more that we're going to look at here. 2 rules here that are similar is the idea of a power rule and then the quotient rule. So Bob, I've given them kind of an idea, but do you want to come up with some examples to explain the power rule and the quotient rule?
Sure. Again, the power rule, an exponent is giving you an idea of how many times a particular quantity is involved in a product. So if I have something like x to the 3rd, I know that is x times x times x. And that's the product of 3 x's, and it's a pretty straightforward rule. It's just simply notation. But if somebody starts to nest the notation, it can sometimes get tricky. So if I put a x to the 3rd and then put a power of 2 on that, then the question is, what does this now become? It's, of course, the thing in parentheses is still just x times x times x. So I now have this situation. And the meaning of this 2 is still the same thing. Whatever is the exponent is applied to, I just need to multiply 2 of them together. That's what that 2 means. So this will be x times x times x times x times x times x. And if we think about kind of a counting game here, could we have predicted how many x's we would have ended up with when we went down this road? And you realize, yeah, sure, there's going to be 3 in every parenthesis set, and there are 2 parentheses sets, so we must end up with a total of 3 times 2, or 6. So the shorthand using the exponents, when you're nesting an exponent within an exponent, ends up being the product of those 2 exponents. The quotient rule is actually a very similar application of that same basic principle if we take into account what the x to the n in the denominator represents. So let's look at the proof of this idea here real quick. Basically what I'm going to do is just rewrite the left-hand side until it looks like the right-hand side. And again, I'm following my algebra rules. But one of the ways to rewrite this is to bring the x to the n to the numerator. And if I bring x to the n to the numerator, what do I need to do to the exponent n? Anybody tell me by typing it in there? What should be the exponent on this x if it represents x to the n in the denominator moved to the numerator? Did I ask that one too quick? Hey, negative n. Yeah, French says negative n, and that's right. If it's an n in the numerator and the denominator, it's going to change sign when I move it to the numerator. So I'm going to have an x to the m, x to the negative n is another way to write this. And now I view this as a product, and the product says add the exponents together. So I will add m and negative n, which is n minus n, which is exactly what I was looking for. So if I have something like 8 to the 3rd over 8 to the 9th, then how many am I going to end up with here? And again, use the formula or just use your practical understanding about the exponents. This is 3/8 in the numerator, 9/8 in the denominator. If I cancel everything that could be canceled, I'll end up with extra in the denominator. In fact, there will end up being 6. when I cancel. And that's the same as, according to our new formula, it should end up being 3 minus 9. And let's see if that works out. What is 8 to the 3 minus 9? That's the same as 8 to the negative 6. And we know that 8 to the negative 6 is another way to write 1 over 8 to the 6. So these all fit. And when we use equality signs here, again, we mean all of these things are exactly equal. They're written in different ways, but one of the goals in algebra is to figure out different ways you can write things so that we can better understand them, often within the context of an application. And we'll get to applications in a little bit.
Wonderful. So that was 2 more rules, and we have just 2 more to continue investigating here. The power of a product rule and the power of a quotient.
Yeah, again, the exponent is telling us how many copies we're going to multiply together of the thing that it's acting on. So when I see xy to the n, that means I've got n copies of xy multiplied together. And I know that's a little abstract. We don't have an exact value there written, but we can think about it in terms of if I have n copies of x times y, here's my question for you. How many copies of x do I have, and how many copies of y do I have? And what this product rule is saying is that we're going to end up with n of each. And if we write this an example, let's just jump to an example. If I have something like 3x to the 5th, then according to the rule, this should end up being 3 to the 5th, n to the 5th, or x to the 5th, sorry. And we could see that work its way out. If I have, again, the 5 means I've got 5 copies of 3x multiplied together. Wishing I had chosen 4. Better than choosing 15. Anyway, there's 5 copies of them. And now if I just go through and count, how many 3s do I have? I got 1, 2, 3, 4, 5. And I realized all the mystery was gone as soon as I wrote it. But that's the same then as 3 raised to the 5th power. And I don't need the parentheses here, but I want to make sure we see that as 5 as the exponent on the 3. And then we have how many x's? The same number, right? They travel in the same pairs. So I end up with x raised to the 5th power here as well. So starting with a product raised to an exponent, each term in that product has the same exponent. All right. And much like the last pair of rules, number 8 down here is a nice pairing on that same fashion. If I have the fraction x over y raised to the n, and I think about multiplying n copies of xy together, how many x's will I end up with in the numerator, and how many y's will I end up with in the denominator? And hopefully that's becoming, that visual is easy to see. There would be n in each spot. So I can rewrite that as x to the n over y to the n. Any questions on that pair?
Okay, I think you explained it rather clearly, Bob. Thank you. So you talked about kind of the application of this, and here I've given you an application problem that is using a lot of the ideas that we've talked about, just kind of mixed together. And so I want you to, the participants there, to work this out. See if you can understand, using these rules we've just gone through, and figure out in the end, after solving this entire thing, and there's multiple ways to solve it, to what degree, okay, or what exponent or what power is the variable q being raised? And I've given you 4 different options. So we'll give you a minute to kind of think through that. Go ahead and pull in when you're ready, and then when you're done with that, we'll have Bob work it out for us and explain how he goes through this one. Go ahead and pull in there when you're ready. A, B, C, or D. What will Q be raised to? So French, go ahead and put that in as a pulled response there. All right, well, in publishing, we do see that a lot of people chose D. Bob, do you want to walk us through that?
No, it's the answer I think I came up with, so hopefully we're all right.
Yeah.
Good job. So I'll go through this fairly quickly, but the one thing I'll comment on briefly is the order in which you do certain operations. When I see this expression here that has something a little complicated going on inside a set of parentheses with an exponent outside, I will pause a moment and think about what order I want to do these operations. And there's more than one that will work. I just tend to look for the easiest, right? We're all intrinsically want to do as few steps as possible. I won't use the word lazy. We're all efficient, right? So I think in this particular case, I would attack this product right in here first. And again, simplifying down that product before I worry about the exponent that's on the outside of the parentheses. So I'm going to do that step first, which means I'm leaving the 2Q7 to the third alone. I'm sorry. It's a 7 there and a third there. And then what I'm going to do is take the product of Q to the third, Q to the minus 2, and I know what I can do there is add the exponents together. So if I add 3 and negative 2, then the exponent on that Q is really a 1. And when the exponent's 1, we don't normally even write it. It's implied to be a 1 if we don't put an exponent there. But I'm going to write it there just as for effect so that we see where that 1 came from. That 1 exponent came from the 3 minus 2. Then the rest of these, we're distributing the exponent across the product. We weren't asked about the constant, but we might as well calculate everything. That 2q to the third would be a 2 to the third, q to the third, plus, or I'm sorry, times, my mouse is slipping, it's a parenthesis, 3 squared, q squared, and there's multiplication going on in there. And now I can rearrange things. I've got a 2 to the
Bob,
third.
I think you missed the idea that q in the original problem was to the 7th power.
Oh, I'm sorry. I can't read my own handwriting. Thank you. Thank you. That should have been a 21 then. Very good. All right. So 2 to the third, 3 squared, q to the 21. I would have discovered a mistake in a moment, but I always can use the help. Q to the 21 q squared. And now we have the product of same base, different exponents, so we can add the exponents. And that's the final step. This piece here would be a q to the 21 plus 2, or 23. Uh-oh. What did everybody pick? Oh, they picked 23. Very good. D.
All right. Fabulous. So that was a little bit about exponents, a lot of rules in this case, and that's, a lot of practice. But one application of some of the exponents we've been talking about is scientific notation. So in our chat feature, go ahead and write something that you might know about scientific notation. Great, saves a lot of zeros. Wonderful. Other things you might know about scientific notation. An application of where scientific notation is used, any mathematics with it. Okay, so we have it saved a lot of zeros. Anything else you might know about scientific notation? Any applications where you've seen scientific notation used? All right, wonderful. Calculating AU, other enormous amounts, and tiny amounts. Wonderful. Okay, so it's used in these applications, and we're going to investigate a little bit more about what exactly is scientific notation, what's the mathematics behind it. So first I want to poll and just see what background knowledge you might have about scientific notation. Let me get the poll set up here. I'm asking you which of the following is not in scientific notation. So I want to see if you've seen it before, if you have any idea what might not be in scientific notation. And this might help lead us to a definition then of what is scientific notation. Okay, so again, use that polling feature to see if you can figure out what is not scientific notation. All right, I am going to publish our poll here. And we'll have Bob talk us through kind of what is scientific notation and what is not scientific notation.
The idea behind scientific notation is it really is a type of notation, which is typically put together to help simplify the way we express numbers. And the polls are exactly right. Sometimes when numbers get very large or very small, we need many digits to represent them, and the sheer size of the string of digits can be overwhelming. So scientific notation is a type of notation that has a particular structure to it, and once you start dealing with it a little bit, it can help you easily spot differences in numbers and understanding things in terms of this new notation. The structure is a man-made thing. We defined it to be a certain way. And it's basically a single digit to the left of the decimal point, and then any number of digits to the right is okay, times 10 to an exponent. And the exponent up here is whatever it needs to be to make the number correct. And the only tricky thing is on this A. That A can't be the number 0. It's going to be a number 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the only possible values. So when you're given a number that's in scientific notation, you can use the multiplication and our understanding of what this exponent means on the 10 to rewrite it in terms of a number that's not in scientific notation. And
all right. Well, let's look closer at that. Again, here is well, a definition. It's kind of hard to explain that the number needs to be between 1 and 10, or really 1 through 9. We know it can't exactly equal 10, and multiplied by a power of 10. So here's some of those conversions then. We're going to convert between what we call standard notation or regular number notation into scientific, and then next we'll look at going from scientific back to standard.
Yeah, so to put this first one into scientific notation, to match that notation I had up there a moment ago, What I really want is a decimal place right in there. And I can't arbitrarily put one in there. So I'm going to think about how I could rewrite this in the form of 3.125. And actually, since I'm to the right of the decimal place, I don't need to write these zeros. They don't mean anything when I'm to the right of the decimal place. So when French typed in there that it saves zeros, those are the zeros French is talking about. But I can't just put equal there because it's certainly 312 million is not the same as 3.125. But if I multiply by the right amount here, I can have equality. So the question is, what exponent do I need to put on this 10 so that my equal sign here is correct? So you want to type that in for me?
All right, see if you can figure out what power of 10 we're multiplying by.
Yeah, what do I need to put right up here on that 10 so that I have equality? All right, seeing a couple of answers come in. And one of the ways to think about this literally is to think about moving that decimal place. If I think of my original number as having a decimal place right there, which we don't typically write it when it's just an integer, but it's not wrong to put it there. What I want to do is move it over in between the 3 and the 1, where my arrow is pointing. And I know that each power of 10 can move my decimal place 1. So I'm looking at a movement of 1, 2, 3, 4, 5, 6, 7, 8. So it takes 8 movements of the decimal place to get it over to here. So if I've got it over here, which is what I've got here, to move it back to where it belongs is going to require 8 multiples of 10. So I have a 10 to the 8th there. So that's exactly right. How about on the next one? Again, I want 5.62 to be my number. The most significant number is this 5, so that's what ends up to the right of the decimal place. But if I really want equality here again, then I've got to move that decimal place, and I'm going to use a power of 10 to do that. But what power of 10 will move my decimal the other direction? Yeah, I see a negative 5 coming in, so let me think. If I wanted to move this one, it would take 1, 2, 3, 4, 5. And I'm going to want to move it, when I'm thinking about this decimal place over here, I want to move it 5 places now, and I want to move it 5 places to the left, which means I'm going to be dividing by 10 5 times, which we now know to mean an exponent of negative 5. Again, 10 to the 10 to the negative 5 is the same as dividing by 10 to the 5, which is moving our decimal place to the left. Very good on that one. You guys were quick.
So now we can also convert between standard notation and scientific notation then.
Yeah, so now we just use our multiplication skills. What does 10 to the 5th mean, and what is 5.08 times 10 to the 5th? And again, if we think about it in terms of multiplication or in terms of moving the decimal point, both of them are pretty quick. I'm going to move that this 5 is going to move my decimal point to the right 5 times, so it's going to be 1, 2, 3, 4, 5. And when I run out of digits, I just backfill with zeros. And again, this sounds like a math trick, but if you just simply write out the various powers of 10 and do the math yourself, 1, 2, 3, 4, looks like I need to go one more, I'll end up with 508,000. Exactly like everybody's typing in, so very good. The negative exponent on the next one, much like the last set of problems, is going to push the decimal place to the other in the other direction. So instead of 4.321, I'll want to move the decimal place 1, 2, 3, 4, and I just front load with zeros to fill in the gaps. So I will end up with 0.00043221. Right? And again, if you think about what I would need to multiply this number that I ended up with to get back to 4.321, it would be exactly 10 to the 4th, which is the opposite sign as this one. So this is dividing by 10 to the 4th. Very good.
Wonderful.
Yeah.
Seems like everyone's understanding scientific notation. Bob, I want to thank you for joining us today. I know that you have to leave to a meeting, so thank you.
All right. Thanks, everybody. Enjoy the rest of the live lecture. Take care.
We're going to continue on just a little bit then, talking about some radical expressions and rational exponents. And there's a lot that we have, that we haven't talked about. This is a fairly large module, but I'll get you into some ideas here. Fractional exponents, we have things raised to a fraction, such as 1/2. So if we think about the idea of the square root of 100, we can write that as 100 to the 1/2 power. Okay, 100 to the 1/2 power. And what that is telling me is that I'm raising 100 to the first power, which we know is itself, but then I'm taking a root or a radical. Okay, and the root I'm taking is the square root. Okay. Looking at this further then, we can see that the cube root of a number, such as 27, can also be rewritten as 27 to the 1/3 power. And we do know that the cube root of 27 is 3. Likewise, if we look at the 1/4 root, we get the 4th root of 16. Or sorry, if we look at 16 raised to the 1/4 power, the 1/4 power then can be rewritten as the 4th root of 16, which is 2. So this is a little bit just about fractional exponents, which really tie into our understanding of roots and radicals. And here's a rule. Lots of rules in this one. If we have some base a raised to a fractional power, m over n, we can see that m is the power that we raise it to. And again, that power that we raise it to can either be inside the radical or outside the radical. And we are taking the nth root of it, okay, whether that n is a square root or a cube root. So, practically looking at this, we have 8 to the 2/3 power. I can look at this in either way that makes sense to me, one of these two ways. 8 to the 2/3 power could say, well, I'm taking 8 squared, and then I'm going to take the cube root of that number. And 8 squared is 64. And then if I had to look, well, what is the cube root then of 64? And the cube root of 64 is 4. So there's one way to look at it. Another way to look at it would say, I'm going to take the cube root of 8, and then I'm going to square this thing. And so the cube root of 8 is 2. And then I can see I have 2 squared, and 2 squared I know is 4. To me personally, I like the second way of writing this. I like to break things down. The cube root of 8 equaling 2 is a lot easier for me to take than a cube root of 64. Now, this rule is also going to help us when we are taking square roots or cube roots of variables. And I know, French, that was a question that you had earlier, was the idea about variables. So let's take a look at this then. And specifically, I'm adding in cube roots. because cube roots can be positive or negative. If we think of having a -2 cubed, okay, a -2 cubed would be a -2 times a -2 times a -2, and a -2 times a -2 is a +4, multiplied by a -2, and we get a -8. Which means if we took the cube root of a -8, or if we had -8 to the 1/3 power, that's going to equal a negative. So when we're working with cube roots, and in fact any odd root, such as fifths or sevenths, we can have negative roots. So in this example, the cube root of a -27 is a -3. Could also look at that as what is -27 to the 1/3 power. And in this next example, we have the cube root of a -x cubed divided by 8. And here's a little bit of where our rules come in. If I look at this, I could also say that this is a -x cubed divided by 8 raised to the 1/3 power. Okay? Well, probably the cube root of 8 equaling 2 is easy to see. And you might think, well, yeah, I know that the cube root of anything cubed is itself. Okay? But the other way to see it is using our power rule. We have 3 to the 1/3 power here. 3 to the 1/3 power is saying when we have a power raised to another power, we multiply. Okay? Meaning 3 times 1/3 is just 1. So that's where we get -x. Okay? So again, we can look at this fractional power, and we can start adding in some kind of more difficult ideas here. For example, 16 over 25 to the -1/2 power. This we could look at as 16 over 25 to the -1/2 power. Well, when we have something raised to a negative power, we want to take the reciprocal of that and raise it to the positive power. Okay, what we could say is this is really 16 to the -1/2 divided by 25 to the -1/2. And then if we remember these negative powers, once in the denominator, we zip that up to the numerator, giving us 25 to the 1/2 power. Over 16 to the 1/2 power. And again, that 1/2 power is telling us take the square root, right? The square root. So what is the square root of 25? And what is the square root of 16? And we see that the square root of 25 is 5 and the square root of 16 is 4. So in this instance, we have 5/4. So now, looking at 27a cubed to the 2/3 power. Again, I'm going to remember 2 is what I'm going to raise this thing to. Okay, but then 3 is going to be my root or my radical. So what this is telling me is I'm going to take the cube root of 27a cubed and then I'm going to raise that whole thing to the 2nd power. So go ahead, see if you can figure out what is the cube root of 27a cubed. And then from there, after you figure out what the cube root of 27a cubed is, go ahead and square that. See if you can't figure that out. Okay, as you're thinking, I'll kind of continue. Good, we have some people maybe figuring it out here. Yeah, 9a squared. So where did you get that? Well, the cube root of 27 is 3, and the cube root of a cubed is a. And so then we have to take that 3a, and we have to square that, getting 9a squared. Perfect. And so, French, I know that you had a question, which I'd like to answer as we're kind of concluding here, and I know we're concluding a little late. But your question was about then, what happens if I'm taking the square root of something like x to the 25th power? Okay. Well, if we're taking the square root of that, then we have to think, well, that's x to the 25th power raised to the 1/2 power. And then we can use our rules of the idea that a power raised to another power, we multiply, or we would get x to the 25/2 power. And that doesn't work out perfectly, but that's definitely not equal x to the 5th power. We're not taking that exponent that we're raising and just taking a square root of it. So another example then might be something like if we have x to the 30th power, and we were taking a cube root of that. Well, what we would say then is that is really x to the 30th to the 1/3 power, and then we can see 30 raised to the 1/3 power, x to the 30 to the 1/3 power to a power we multiply, that would be x to the 10th power. And that should also make sense because if we're taking a cube root, we're looking for something multiplied 3 times to give us that x to the 30th. And what multiplies 3 times is x to the 10th. Okay, so there's just a little further explanation then of how we can take roots of variables. So with that, I think I'll conclude. There are some more ideas out there that we didn't cover, but that's the fun of going through the learning objects and the rest of the Math MOOC. So if you have any further questions, I'm here to answer them. If not, I hope you have a fabulous day as we are really moving forward with our math journey here.